Hello, my name's Kevin Porman, and today on codeLive we're going to be tackling the second most popular requested topic I've gotten. I've always asked people if there's something they want to learn about, let me know in the chat. So today, if you're tuning in, let me know what you'd like to learn about in the chat. But one of the things that often comes up is everything sort of surrounding encryption and secure data transfer. And so today we're going to be tackling a lovely class and some tests that were written by my colleague, Alba Rivas. Alba, you want to say something?
Hello, everyone. Thank you so much for joining this codeLive. And thank you so much, Kevin, for inviting me. This is going to be my first codeLive with you, and I'm super excited.
Yeah, this is great. Now, as a little backstory here, about, I don't know, 2 months ago, you were like, hey, I'm writing this blog post on encryption techniques. And I was like, that's awesome, but you know what you really should do? You should put it into Apex Recipes. And Alba was like, okay, I got that. We can do that. And so she wrote Encryption Recipes as a class and Encryption Recipes tests. And today, because this is a popular topic, we're going to go over and we're going to flip back and forth between her blog post that she wrote and the code here. And we're going to walk through it and talk about what encryption, when we say encryption, what all that encompasses, and what the various terminology pieces mean, etc. And so I thought we would start over on the blog post, ye old blog post. Now, I asked Sarah to tune us in and drop the link to the blog post there, and I see she did that in the chat. This is the blog post itself here, and I'm going to skip. We're not going to read it to you. That wouldn't be terribly exciting, but we do want to draw your attention to certain things in this blog post that are really key. And that is that we're going to start with these first 4 definitions of things. So the first one is confidentiality or secrecy. Now, Alba, when you think of confidentiality, I don't know about you, but here when you join a company and one of the very first things you have to do is HR makes you sign the confidentiality agreement, and that is that you're going to keep secret all the secrets of the company, basically.
Exactly. That's the point, that the information that you transmit to a third-party system,
Yep,
or from a third-party system to Salesforce is secret, is impossible to guess in that way that the information has to follow, right?
Right. And this is generally, when we talk about this stuff, we're generally talking about encrypting things for transmission, right? Because if we're talking about encrypting data at rest, we have solutions like Platform Shield in order to do that. So that when we talk about encryption today, we're largely talking about encrypting data for the transmission over a system that we don't necessarily trust. So whether that's the internet or carrier pigeon, there's always the April Fool's joke about 802.11p for carrier pigeon and Wi-Fi over pigeon, but we don't trust this, and so we're going to encrypt the data so that its secrecy, its confidentiality is maintained. But along with that, we also have these 3 other concepts called integrity, authenticity, and non-repudiation. And I have to admit, when I read non-repudiation, I had to read that a few times because I wasn't entirely sure I'd ever heard that phrase before. I understand the concept, but I'd never seen that phrase before. But let's start with integrity. When I think of integrity, I think of the things that I'm trying to teach my kids. I want my kids to have integrity. But when we talk about it in this context, we're saying that the message is fundamentally exactly what was sent. Is that fair?
Yeah, exactly. It means that the message has not been tampered with, that there wasn't someone in the middle who changed the message.
Change it, yeah.
Right.
And that's super important because we want to make sure that when we decrypt our data, that we're getting back the data that was actually sent, right? Now, if you've ever played Telephone, do you remember this game? Do you have the same, Alba? I always talk about it as if everybody understands these cultural artifacts.
We do.
Yeah, Telephone. So if you've never played Telephone before, what it is you get somebody to say a phrase into the next person's ear, and then they go all the way through the classroom or the group, and then at the end, the last person stands up and says, well, the message was X. And everybody has a good giggle because that was definitely not what was originally sent. So integrity solves that by ensuring that by the time the message gets to the end user, it is exactly what was sent. Now, on the other hand, You can have something that is confidential and has integrity, but there's no guarantee of who sent it. And so we have authenticity, and the authenticity is a way of saying, I, Kevin Poorman, sent this message, or I, Alba, sent this message. Why would that matter?
Because sometimes you need to be sure that the person that's sending you the message is the person who's meant to be, because sometimes it may happen that someone else tries to impersonate that person, and it's an attacker that sends you something which is not, which is dangerous, right?
Yeah, so this is the email problem, right? We all get emails, and it's an email, and it looks almost perfect, and it says it's from Facebook and talking about my account's been compromised. Click here to reset my password. But then I check a little bit deeper, and I realize it's not actually from Facebook. That authenticity bit is key. And then finally, we have non-repudiation. And why don't you explain that one to us?
Yeah, so non-repudiation is kind of a stronger concept than authenticity, because it ensures, like, legally, that the sender is who is meant to be. There is a legal proof that the sender is that person. And we are going to see one algorithm, which is digital signatures, that are normally used to ensure non-repudiation, and digital signatures are used all over the place for legal processes, right? If you, I don't know in the US, but here in Spain, if you need to do some administrative tasks with your identity card and you want to do that virtually, you need a certificate, and you need to digital sign the documents that you are going to send, right?
Gotcha. That's pretty cool. We don't have anything near that fancy where I live. We still have to go downtown and show up with documents and everything. Anyway, so we have these 4 key concepts here. Now, when we talk about encryption, technically the phrase encryption, the word encryption, generally only refers to confidentiality or secrecy. When we encrypt a piece of data, we're turning it from something that is plain text that we can read, or an image that is we can see and make sense of, into something that is encrypted, something that is hidden, or I feel like this would be a great place to be like, and the word encryption means, but I don't have any of that. But the whole like encrypted idea is that it's now secret and hidden away. And when we say encryption, that's technically what that refers to, but we're going to be expanding it to talk about all 4 of these concepts here today. And one of the things that we really like about the Apex platform, or the Salesforce platform, is that the Apex has a crypto class built in, and it's got a lot of pre-built functionality for you. And we're going to walk through that with some code here in a little bit. But before we get to that, let's talk about AES encryption. AES stands for Advanced Encryption System, because naming is hard. Anyway, the Advanced Encryption System is a set of algorithms to encrypt data and decrypt data. And when we take a look at how it works, there's all sorts of details about how it functions in terms of whether it's a block of fixed text or streams or all that sort of stuff. But regardless of what it is, AES is the preferred method for taking a bit of plain text and turning it into something that is encrypted. Now, when you were doing the encryption recipes, Alba, I noticed that you did things with AES encryption. Are there other algorithms that are available to us on the platform?
So for encryption itself, no. For encryption, we only have the AES encryption, and we have 2 different options to use it or to implement it, which are one option, generating our own initialization vector, which is something that we are going to need for the algorithm. And the other option is to use an initialization vector that is generated automatically by Salesforce, by the method that the crypto class provides. But there are no other encryption algorithms in the crypto class. We are going to see that there are 3 different options for hashing and creating signatures, but for encryption, we only have this one.
Yeah, and I really like the way Alba put this diagram together. There's this one, and then there's this one down here, and they go over the same idea. And what she's showing here is this initialization vector. And this initialization vector, I'm trying to come up with a great way to explain what an initialization vector is, because it's not necessarily the password to decrypt your message. It's sort of a ride-along bit of information that the algorithm uses to initialize its key components. Now, when you talked about having the encrypted with managed IV versus encrypted with the initialization vector, the difference is who generates that initialization vector, right?
Exactly.
Okay.
So if you use the method that doesn't create the initialization vector for you, I think it's crypto.encrypt. In that case, it's you, the person who is in charge of generating that initialization vector and sending it to the receiver, because the receiver needs to have the initialization vector to be able to decrypt the message. But if you use the method that it's called encrypt with managed IV, right? In that case, Salesforce is going to generate that initialization vector for you and is going to send it to the receiver as part of the message. It's going to be the 128 first bits of the message. And then the receiver can rescue that initialization vector from the message and use it for decryption, right?
Yeah. And the way I like to think about the initialization vector is it is attached to your message to the receiver, and it is attached in a way that it allows both ends to be dealing with the same set of variables for the algorithm. So you can think of it as not a password to decrypt things, but a set of variables needed for the algorithm, and you send those along with it so that the receiver can understand how the algorithm was used in order to encrypt it and therefore decrypt it. So that is a lot of... Go ahead.
Yeah, exactly. And on top of the initialization vector, the other item that we need to know about the AES algorithm is a pair of symmetric keys that are shared with the receivers. This means that the sender encrypts the message with a key, and then the receiver needs to have that same key to be able to decrypt the message. And obviously, those keys needs to be shared in a way that's secure, right?
Right. Now, Alba, you said the word symmetric. For those of you who've never heard that before, symmetric encryption is where the key used to encrypt it is also the key used to decrypt it, the message. And when you have asymmetric encryption, the key used to encrypt it can't do anything but encrypt things. You have to have a different key, a decryption key, in order to decrypt it. And typically those are public and private key pairs. So you may hear that phrase thrown around. But an AES is a symmetric algorithm. And so you're going to have both ends of this. If Alba and I were sending encrypted messages back and forth, we would have to have say securely met in person and exchanged the file that is the key, and then either one of us can use that key to encrypt a message, and with the platform's crypto class, it will automatically inject that initialization vector for us, or IV, and send it on to the next person. And I, receiving that, would be able to take that and say, okay, platform, decrypt this for me. It's already got the IV passed in from the receiver, and here's the key I have, and it'll be able to decrypt it using those things. So that's pretty cool. Now, we've seen a lot of theory and some vocabulary here, and we are almost 15 minutes into this, and we haven't shown you any code. And shame on me. So let's go ahead and switch over to Visual Studio Code. And this is our Encryption Recipes class. We've got a lot of different methods in here. And what I wanted to do is hopefully talk through these recipes and describe what they're doing, and then we can run our tests, look at the tests to see how these methods would actually be used. And again, we're calling the crypto class here, so a lot of this is syntactic sugar on what stuff the crypto class is already doing for you.
Yes, so for instance, we can start talking about this method here. Hopefully you can see it highlighted in the screen, right?
Yep.
Okay, it's my first time with live share, and this is super exciting. So this method, encrypt AES256 with manage IV recipe. Basically, what I'm doing is to call the crypto class dot encrypt with manage IV method, which is the one in which Salesforce generates the initialization vector. By the way, we strongly recommend to use this method, right? Because it's easier than having to manage your own vector. We also created a series of enums to be able to set which algorithm you want to use, for instance, right? And for the other algorithms too, to make it easier if you want to use Apex recipes. But this is basically the name of the algorithm. In this case, we are picking the one that uses 256 bits. Normally, the bigger the number of bits, the more secure the algorithm is going to be. What happens is that also it's going to take more time to execute. So it's a balance and a compromise that you need to evaluate, right?
I want to insert just a little something there. Generally, the higher number of bits, the more secure it is within the same algorithm family. So it's fair to say that AES 128 is less secure than AES 256. However, comparing AES 256 against, say, Blowfish or Triple Des, that's a completely apples to oranges comparison. That doesn't make sense. But when you're talking about the same algorithm, you can always compare and go, okay, well, should I go up one more notch? Should I use the max? Should I use something lesser than that? And again, like Alba says, it's a trade-off.
Yes, exactly. So basically, well, these algorithms always receive a blob because they receive binary data. If you want to transform, for instance, from a string to a blob value, you can do something like this, blob.value of, right, to transform the data. And then we pass the data to the crypto class method. Now just that, right?
Yeah, and you also have a constant in here for the AES key. And I just want to scroll up here because I want to draw your attention, everyone, to this comment right here. Keys are here for testing purposes only. Never do this. This is a key that we've generated that is technically valid, but it is also not valid because it's not tied to anything. And so when you see this, these things in here, never put your key in this. Pull it out of Shield, pull it out of something secure. Don't put it in your class. This is only here because we have to have something like this in order to generate and test these things. Now it happens that we can cheat with the AES key because there's a method on crypto to generate the AES key. But some of these in here, like HMAC key, etc., don't put them in the code. Pull them out of secure storage.
Yes, exactly. So this is only for testing purposes. So we have the encrypt method, and equivalently we have the decrypt method. Basically, is the same usage, right? We use the method, setting the name of the algorithm that we want to use, the symmetric key. Look here that the key is exactly the same one, the key that we are using in the encryption operation and in the decryption operation, and then the data to decrypt, which is the data that has arrived to the receiver, right? Here we have the two methods in the same class, but obviously in a real use case, one of the methods is going to be normally in Salesforce, and the other method is going to be in the receiver. There are libraries written in Java, in Node, etc., that are going to let you implement these algorithms in other languages.
And those libraries, even though they're in different programming languages and even different platforms, because the algorithm is the same, you can send a message from Salesforce encrypted with a AES key, and then in Node or in Java or in Python or Ruby or C# on Windows or Linux or Mac, and still decrypt it just the same, because all the algorithms are the same regardless of their implementation language.
Yeah, indeed. In the blog post, I added links to some implementations of this method done in, I think it was in C++ and JavaScript. So
Nice.
you can take a look at those examples. So should we take a look at the test class, Kevin?
Yeah, let's go ahead and take a look at the test class.
Okay. So here in the test class, we have a method that tries to test the full use case, right? What happens when we encrypt some data, we send that data, we emulate that, we send that data over an insecure channel, and then we decrypt the data in the receiver. So basically here we are using a string that we want to transmit. Here is just test data. I'm not original. I'm sure that Kevin would have used something much more fun, but I just decided to use test data. And what we do is to transform it to blob format, because we need to pass the information to those methods in binary format. Then we call our encryption recipes method to encrypt the data with a managed initialization vector. And then remember that when the data is sent, that initialization vector is going to be sent as part of the message. And then we are able to decrypt the data and make sure, assert here, that the data that we sent and that we encrypted is exactly the same as the data that we receive and that we convert back to a string, right?
And so this is, again, this is the sort of simplest possible round-trip path for encrypting and then decrypting data. And I want to draw your attention to two things here. One, because our encryption recipes generates that AES key every time you initialize that class, it's that key is only going to be valid for that transaction. So if we were to encrypt this and then throw this in a at future or a queuable class, that would fail because the key would be different. All right, so just keep that in mind. And I also want to draw your attention to something that Alba does that I think is really cool, and that is that she structures her tests as given, when, and then. And the way that works is, this is the data you're going to set up needed for your test, and this is what happens when you run your test, your tested code, and then you're going to verify your code. And that's a really simple and straightforward way of thinking about writing your unit tests. I tend to, it was ingrained in me from an early age that I needed to create my test data and then do all these different steps, and you've boiled it down to 3 that makes it really simple, and I really appreciate that. So kudos on that. Let's just run our unit test here just to demonstrate that this does in fact do what we state that it does. And this would be an opportune time for a failure, but there we go. We got it working. Encryption recipes ran just fine, passed. So we have sort of encrypted and decrypted. And again, when we talk about encryption recipes, we're covering 4 different things there. So we've got the secrecy aspect, and that's sort of the simplest thing to do, because the platform does all the heavy lifting for encrypting and handling the IV and all that sort of stuff. What's our sort of next step, Alba? How do we take our encrypted text and then start to make it useful as we pass it over the wire?
Yeah, exactly. So one thing is encryption, right? And the other thing that we want to talk about today is how to hash your data or how to sign your data. This is a different concept. So those are separate concepts. You can encrypt your data and don't worry about hashes, or you can hash your data and don't worry about encryption and pass your data in plain, right? With no encryption. But ideally, the most secure combination would be to have both, right? To have on one hand the data encrypted, and on the other hand the data hashed, so that its integrity or also authenticity and non-repudiation, depending on the level of security that you need, are ensured too.
And just so that everyone's on the same page here, when we say hash, we're specifically talking about a way of taking any sort of data and running it through an encryption algorithm that is one way only, meaning that we're not going to be able to take this algorithm and the encrypted data and unencrypt it or decrypt it. This is a one-way hash. All right, so we're gonna, and typically your hash functions take a vast amount of data and then return to you a hash string that is much shorter. So if you think about the classic MD5 hash method, what you get out of that is, if you always get a 32 characters is 64. You get a relatively short string, and you can take something, the length of War and Peace, and hash that, and you'll get a certain character string. And what that hash algorithm guarantees is that no other data will ever collapse down to that same hash string, in theory.
Yeah, exactly. So with encryption, you can encrypt and decrypt. With hashing, what happens is that on the sender, you generate a hash, which is this small summary of the message that you want to send that has been obtained through an algorithm, right? And then in the receiver, you are able to execute the same hashing algorithm to obtain a second hash that needs to match with the one sent by the sender, to make sure that no one tampered with the message, right?
And if this sounds very familiar to you, if you've ever sat down and written a login system, this is the right way to build that kind of thing. Because what you do is you take the input from the user, whatever it is, and you hash it. And then you store that hash, knowing that you can never decrypt that hash in order to get back to what they actually type in for the password. And so later when they go to log in, you hash their typed in password, and you compare their newly typed in hash to the existing hash in the database. And that's how hashes are used. So as we talk about hashing on the Salesforce platform, I'm going to scroll down here to the next diagram. Now we've got 4 different hash algorithms on the Salesforce platform. Am I calculating that right?
I think we have 3, right?
3?
I mean, are you talking exclusively about hashing?
Yeah, just hashing.
Okay, so we have MD5, HMAC 256, and 512. Those are the 4 that we have. Yes.
Yeah. So we've got, MD5, we talked about that one before. The SHA, or SHA-1, SHA-256, and SHA-512, these are the same algorithm, but with different bits of data that'll be returned. So remember I said MD5. Mm-hmm. I want to say it's a 64 character string. Don't quote me on that. But if you've got, your SHA-512, you're going to get more data back than the SHA-1 string. The other thing you have to keep in mind is the larger the number there, the less likely you're going to end up with a collision. And while collisions are mathematically extremely rare, they can happen. And that's why when we see collisions happen, that's when we tend to say, don't use MD5, don't use SHA-1, because collisions have occurred and we don't want collisions, where the same data can generate, different data can generate the same hash value. So why would we want to use a hash? What does a hash give us when we're sending data? And do we have to encrypt before we hash, or how does that work?
So depending on the algorithm or the approach that you decide to take, if you don't encrypt the hash, then you are only preserving or ensuring integrity. If you do encrypt the hash, that's done with HMACs, right? That preserves integrity and authenticity. And
okay.
We're going to talk about that later. But Kevin, do you want to explain, because I think it's an important concept, how to compare in the receiver that the hash that was received is equal to the one that you have calculated? So
I think I know what you're getting to, but I'm going to switch us back over to the code, and I'm going to let you show us in the code base.
Okay, perfect. So if we go back to our encryption recipes class, well, you are going to find another recipe to encrypt with a custom initialization vector if you want to take a look, but I'm not going to stop on that, and I'm going to try to find our hash recipe. So here we have our hash recipe, right? In the sender, it's easy because the only thing that we need to do is to call the generate digest method passing in the name of the algorithm that we want to use. Remember, the bigger the number of bits, the more secure will be, and the data that we need to hash, right? Then we are in charge of sending to the receiver two things. We need to send the data, and we need to send the hash, because they need the hash to do that comparison. But pay attention here, because this is the most interesting part of this recipe. How do we recalculate that hash in the receiver, and how do we compare those digests to be sure that the message has not been tampered with? So, well, regenerating the digest is super easy, because we need to do exactly the same, right?
Yeah.
With the data that we need to check, we define the name of the algorithm, and that's it. But then it's important to compare the two hashes using an R equals constant time function.
All right, I'll bite. What is an equals constant time function?
Okay, so imagine that depending on the strings that I want to compare, depending on the strings that I have to compare, these functions, the comparison function, takes less or more time. For instance, if I need to compare two strings, two particular strings, right? In a particular case, it takes 10 milliseconds to execute. But if I need to compare another set of strings, it takes 12 milliseconds to execute. That gives information to the attacker, in this case, about the strings that are being compared, right? So the idea is to have a function that always takes the same time to compare the strings,
Gotcha.
No matter the content of the string.
Because
right?
theoretically, an attacker could take and just start throwing lots of data at a hash function, trying to get back a timing idea of, knowing that how long it legit took to decrypt or to hash the legit payload. Trying to figure out what kinds of things are in there to try and get it to around the same time. That helps them narrow down their attack vector. So, okay, constant time. How do we calculate the constant time? How do we do that?
Yeah, so here in Apex recipes, you can find an example of function that always takes the same time to execute the comparison between this first string and the second string, right? What we do is, instead of breaking when the comparison is found, we continue executing the loop always till the end. Right?
Ah, okay. So this is sort of unoptimized by intention.
Exactly.
Yeah, okay. So that's interesting. I like how this is done. So you're going to say, I'm just going to read through this algorithm, make sure I'm following it. So if the first length is not equal to the second length, we're going to bail because it's false. They're not the same. And then if the first length is greater than the second length, wait, hold on a second. If the first length is greater than the second length, then shouldn't we have already bailed?
We are trying to find the maximum length, so that we execute the for loop till the maximum length.
But shouldn't we have already bailed if we've done this one, if the two lengths don't match? Oh no, because we haven't returned. You're right. I was reading result is false, and it's not return, it's
yes.
result. Okay, I'm with you now.
Yes.
I need more coffee. Okay, and then we've got, and we're going to go over each of these elements for the longest string, comparing the two substring elements. Okay, that makes sense. It took me a second, but I got there. I got there. So one of the key takeaways that I want to pass on to all of you is this stuff can be hard to wrap your mind around. Like when I was thinking about encrypting and decrypting things, I never would have thought about timing attacks and how we have to go over each of these characters one by one so that the comparison takes an equal amount of time regardless of what I'm throwing at it. I never would have thought of that. We actually, Alba wrote this, and then we engaged some of the people who are much nerdier about encryption than we are, and we went back and forth to them for a couple weeks trying to get all this stuff right. And what I want you to take away from all that is this is hard, and what we've given you here in the encryption recipes part of Apex Recipes is a good starting point. A good starting point for you to become familiar with how all this works, what these things do, and a good starting point that gives you an idea of where you should start with things in your org. And you should then turn around and engage your product security, your trust team, your encryption nerds that work with you and your org to find the perfect set of compromises for things that you need and the perfect set of tuned responses and tuned methods here. This is insofar as Apex Recipes is a sort of best practice guide to how to do things in Apex, this is a best practice getting started guide. And I want to be very clear on that. You should never just adopt anything from Apex Recipes into your org and just run with it, but you should definitely run this past your product security teams before you start doing things with encryption on either your own product or in your org. Okay, I'll get off my soapbox there. So we've compared the algorithm. We've compared in constant time our hash, and when we do our hash, if we hash the hash and the encrypted payload, then we get, what do we get? I'm confused there.
You are taking a look at the check hash method?
Well, you were saying earlier that if we took our payload that was encrypted and we send that along with a hash, then what we've proven is that that the message has integrity. But you said there was another way to do this where we get the authenticity and integrity?
Yeah, exactly. So to get authenticity, then we can take a look at another kind of algorithms, which are HMAC, right? Let me...
I'm trying to remember what HMAC stands for.
Yeah. So with HMAC, what happens is that we are implementing a hashing algorithm, but we are using a pair of asymmetric keys to encrypt the digest that is generated. It's not really encrypt. This is a nuance that one of the engineers explained to me. It's not a proper encryption. It's really that it is used to generate that hashing, that hash digest. But in my mind, that I try to simplify this kind of thing so that the audience understands, is like if it was encrypted, right? And then you have to use the asymmetric key in the receiver to generate that hash digest again, and then you compare them in the same way. In this case, we don't have to use the R equals constant time functions because the crypto class already includes a method which helps you verifying that HMAC and which does it with constant time.
Gotcha. Okay.
You don't have to implement that, right? And so that you know, HMAC stands for hash-based message authentication code. Okay.
You know, as computer scientists, we love our acronyms.
Maybe, Kevin, if you show the diagram in the blog post, it's going to be clearer for the audience. Yeah. So that I was confused because I'm reading now in the blog post that it is a symmetric key, not an asymmetric key. So sorry, my bad. Too many things in my mind at the moment, but there you see it perfectly. So what happens is that the HMAC one is generated using the key, right? And the receiver needs to have the key to be able to generate that HMAC again and then do the comparison.
So this is basically, I know you just said HMAC wasn't really encryption, but it's sort of encrypting your encrypted message with a second layer of encryption that verifies that the encrypted message of the first encryption is both authentic and has integrity before you decrypt the second message, which is your actual payload. Is this like encryption all the way down?
Yes, in these diagrams, I'm not encrypting the message that's sent.
Oh, gotcha.
I have a note here that I'm not encrypting the message, but ideally, if you want to have confidentiality, you would need to encrypt the message too.
So would you make that? Would you take the hash, or excuse me, the message, and HMAC it, and then encrypt the HMAC message, or would you encrypt your message, HMAC the encrypted message, and send that?
No. The message, if you want to encrypt it, you have to use the first method that we saw at the beginning, the AES encryption for that. Okay. And that's like a separate operation. And then to generate the HMAC, we use a key, a symmetric key, that is going to generate that hash, but which is kind of an encrypted hash. And then in the receiver, you are going to need to have that key to be able to decrypt, not to decrypt, but to generate the HMAC on the receiver so that you can compare them and make sure that the integrity and authenticity, in this case, authenticity too, because having the key means that the person who sent the message has the key as well, right? And that way you are going to check or to ensure integrity and authenticity. So those are like two different concepts, two separate concepts: encryption of the message itself, and then how you generate the HMAC.
Yeah, I'm sorry. I was trying to think about how I would do this if I wanted to send the message. So this little envelope here as an encrypted blob of data. Would I encrypt this first, or would I go through the process of creating the message in the HMAC and then encrypt the message?
Okay. I think I would encrypt the message apart, right? It depends on how you want to do it, but I think I would do it that way.
Yeah, you would do it up here. That's where I was thinking I'd do it. Mm-hmm. Yeah, encrypt the message, then generate a HMAC of the encrypted message, send those over the wire. The HMAC is decrypted, showing that we have we can trust the integrity and authenticity of the message, and then knowing that I can trust the integrity and authenticity of the message, then I would decrypt it.
Yeah, you're right, Kevin. Indeed, I'm taking a look because we did a similar example, but encrypting and signing a message that we're going to talk about that in a second. And I'm seeing that we did it that way. Okay. So yes, that's the correct way to do that.
Okay. So we've covered hashing, we've covered authenticating or HMACing. And then our next step is the anti-repudiation, which sort of is our maximum security, everything is awesome sort of situation. How does the non-repudiation thing work here? How does this work?
Okay, so the non-repudiation, as we mentioned at the beginning, means that there is a legal proof that the message was sent by the user who is supposed to have sent the message, right? So for that, we run a bit more complex algorithm. Is the most complex algorithm of those that we have seen today, right? And in this case is when we use the private and public key, the asymmetric key. That is where I was confusing. I was confusing with the previous use case, the HMAC, right? And why it is more secure this way? Because when you use an asymmetric key in which there is a private and a public key, you don't have to share your private key with anyone. Your private key, you are the only person who has that private key, right? And that means that no one else can say that they are signing the message as if they were you, right? In the other case, in the hashing, it's pretty secure, right? Because you have to share your public keys and your symmetric keys, and if you do that in a good way, in a secure way, it's not supposed to be tampered,
Right.
and the authenticity of the message is supposed to be ensured. But in this case, it's even more secure because your private key is not going to be shared with anyone.
Yeah. So if you've ever, asymmetric encryption is a completely different beast than symmetric encryption. And like I said earlier, the symmetric means you use the same key to encrypt and decrypt, whereas in asymmetric, one key can only encrypt and the other key can only decrypt. And like Alba, you were saying, you're only going to share your public key, and that's the one that can decrypt, can encrypt. Your public key can only encrypt. And so if you want to decrypt it, you have to have the private key. And if you've ever done, let's see, what is it called? PGP or OpenPGP. These are ways of doing a method signature and signing an email, for instance. If you want to do that, you can use those tools, or sign a Git commit. You can sign a Git commit with with that kind of public key. And then the only people that can decrypt it are the Git committers, auditors, or the person you sent the email to. And the way you do that is by exchanging those keys. So when we talk about this digital signature bit, this is our most advanced because we're sort of combining both symmetric encryption for the AES bit and the asymmetric encryption, so that only the intended receiver can decrypt it at all. Yeah.
Yes. Here in the code, it's very clear how it works, because we see that for signing the message, we need the private key of the sender. And for verifying the signature, we need the public key of the sender, which needs to have been shared with the receiver, right?
Right.
The private key is something that you only have, so there is a legal proof that you are the person who has sent this message. And normally, with these algorithms, what happens is that the security increases. So normally, if the algorithm ensures non-repudiation, it means that it ensures authenticity and also integrity, right?
So this is our sort of all-in-one blue plate special of encrypting the data for transfer, ensuring its authenticity, ensuring its integrity, and ensuring that only the intended receiver and only the actual sender could have sent that message or received that message. So how do we go about doing that? It seems like that's a complicated process. So we're going to have encrypt and sign data, and it looks like we're doing the encryption with the managed IV, like we were talking about before. As we walk through this, so we're going to get our encrypted data, and then how do we go about signing it?
So here, what we are doing is to first encrypt the data with AES, indeed with the most secure version of the algorithm. Then we are signing the data with our private key, same as in the previous example, but this time what we are doing is to encrypt the data too. And what we did for this example was to create a wrapper in which you send the encrypted data and the signature. So then the receiver needs to decrypt the data and check that the signature is correct. How do you do that? Yeah, exactly. So how do we do that? We have a crypto verify method in the crypto class, to which you can pass the public key and the signature and the data that you need to decrypt and check. And this is going to tell you if the digital signing part is correct. And then once you are sure that the message has not been repudiated, then what you can do is to execute the decryption algorithm to retrieve the plain data back, right?
I like it. So this, Alba, help me understand here, because when I think about using this and securing communication between Salesforce and even a service I own, rather some third-party service, whether or not I wrote it or own it, or it's somebody that I'm some API that I'm paying for. Part of me wants to be like, why wouldn't I just encrypt and sign every message I send, and expect that every message I receive to be encrypted and signed?
Yeah, I don't think that you have to encrypt all the messages. What you need to encrypt is the confidential data. So if you are sending something that needs to be secured, like for instance, personal data information, or I don't know, your ID number or credit card data, then that data needs to be encrypted. But not all data that you send to a third party needs to be encrypted, only the data that is sensitive.
I guess that's fair. I guess it's fair. My rubric for understanding whether or not the data is sensitive is whether or not I would want my name and that piece of data related to me put on a billboard. Right. So if it's my name and then my social security number, I want that encrypted. If it's my name and what I ate for dinner last night, I probably don't care. Right. So that's sort of the way I think about it. So we can do this round trip though. We can encrypt and sign, and we can decrypt, and we can check the signature and then decrypt, if that works out. Is there anything else we need to think about or keep in mind when we're doing this encryption work? And we have about 10 minutes left, so I'm going to drop a line here into the followers on the stream. If you have questions about this, or comments, or snide remarks, or etc., feel free to throw them in there. And as always, if you've got an idea for what you would like to learn more about, feel free to let us know in the chat as well. So Alba, what else do we need to keep in mind when doing this kind of work?
Yeah, so, well, one thing that we need to keep in mind is the compromise between the algorithm that you select to use and the time that it takes. That is something that I mentioned at the beginning. The more complex the algorithm, the more time is going to take, and that is something that you need to evaluate, right? Indeed, I think that for the signature algorithm, you need to choose between two different families of algorithms, and I read about that, but choosing one or the other had also its own implications. And what I recommend in the blog post is, if you need to implement a signature algorithm, then take a look at the pros and cons of picking one or the other, right? But there are certain considerations that you need to take into account, of course, as with every choice that we do in the platform. And not much more, Kevin. I really enjoyed. Sorry, I have my cats having a fight right there, so maybe
Very nice.
You're listening to me.
Very nice. It's always a good episode when we get the cats involved.
I enjoyed a lot working on this topic because I really like security, and I had the lack of working with these security engineers from Salesforce who are like really smart and helped me a lot. And I think these blog posts and these recipes are going to help people, because I have received also some requests to work on these topics because people wanted to know more on top of what's in the help.
Yeah, that's really cool. Now, just to throw out a little bit of lore here, these digital signature algorithms, there's two of them, the RSA family and the ECDSA family. They have the different bits of entropy, 512, 384, etc. Now, just as a fun thing, RSA is the initials of the three men who developed that algorithm, and they run the RSA Corporation, at least they did at one point. This ECDSA is sort of a next generation one. The benefit it brings you is that your keys are much smaller. So while you'll have the different entropy sizes here. The actual key sizes are much smaller. So like for instance, when I generate an SSH key, I use the ECDSA and I'll get an SSH key that's fairly short. Whereas if I do an RSA 512 key, for instance, then I end up with something that is on the order of like a page of text. Regardless of the size of the key, they are equally secure, but the smaller keys do help to calculate faster. So just a bit of lore there. I'm trying to remember the names of R, S, and A, and I'm drawing a blank. But at one point I knew them. There's a guy whose name I'm now drawing a blank on as well, who's sort of the grandfather of all things security in crypto, Bruce Shiner on the interwebs. If you look him up, he's got an email digest he sends out once a month called Crypto, and he goes over all sorts of this stuff as these new algorithms come out and that sort of stuff. Highly recommend that to you if you are remotely as nerdy about this as Alba and I are. With that said, I've got 5 minutes left. I don't have any comments, questions, or Snyder marks in the chat. So what I'm going to do is I'm going to sign us off just a little bit early today. Thank you all for tuning in, and come back next week. We're going to be talking about custom assertions and Salesforce unit testing. So that'll be super exciting, I promise. And thank you all for tuning in. Thank you, Alba, for joining us.
Thank you. Bye.